enormous evidence from the success in the past that the rules exist and may be discovered, but we should bear in mind that that's an hypothesis and always will be. We can't know otherwise. Discoveries are established by the weight of empirical evidence, despite the fact that we get situated to theoretical concepts. Every branch of science, I believe, has a working model, and it has active research aimed at improving that model, that is to say, to improve it by successive approximation. Our working hypothesis is that this project in each branch will prosper, we will find new rules, and that these rules will converge to one universal set of rules that will discover natural science. Again, an assumption. Whether or not there is a bottom floor, there a final theory, is not at all relevant, I think, to any of us or any of our descendants for many years. We are still working very hard on bringing all of these subjects together and enriching them. So, I begin by reminding about the simplest you could imagine and are consistent with easy versions of inflation, but you can think of many other alternatives, and in which you have applied general relativity theory, for which the precision tests extend to the solar system, maybe 10 to the 13 centimeters, apply it on the scale of the Hubble length, 10 to the 28 centimeters, an extrapolation of 15 orders of magnitude. It is truly an impressive thought that you should attempt even to do that, and even mind-boggling to consider that you would trust the result. But of course, we do trust the result because we have now a tight network of measurements that cross-check each other to rule out systematic errors and that quite persuasively point to this standard model. Not as absolute reality, I must insist, but by the historical precedent, a useful approximation for which we will build and find a still better approximation. But one thing is to be noticed. If there is a better theory for cosmology, and I'm thinking after baryosynthesis, we can know one thing for sure. This new cosmology will predict a universe that looks very much like lambda CDM. That is because the cosmological tests I'll briefly review look at the universe from many sides and find that it is consistent with lambda CDM. So let us begin first by recalling that the universe is very clumpy on small scales. Here is a map of the distribution of galaxies to redshift maybe 7% of the velocity of light. Highly irregular. There are two ways of thinking of the effect of this irregularity on the evolution of the universe in a sort of duality. One approach is to divide in the early universe into a space into small volume elements. In each volume element, use Ray Choudhury's elegant equation to find expansion in terms of mass density, shear, maybe the D'Alembert of the pressure. Follow that evolution to the present and then average across this distribution. That is a very difficult game. It's going to be fascinating to see how it turns out. There is a duality, however. Go the other direction. Start with Friedmann-Lemaitre. Then notice that these density fluctuations correspond to fluctuations from Friedmann-Lemaitre on the order of V over c squared, let us say a part in 10 to the fifth. Consider, for example, that the air in this room has a mass density some 10 orders of magnitude greater than cosmic mean. Spectacularly nonlinear situation. But the gravitational potential in this room relative to the large-scale distribution is a part in 10 to the fifth. That small perturbation means that you may well prosper by starting with homogeneity, adding a perturbation, part in 10 to the fifth, and doing linear perturbation theory, and then second-order perturbation theory that you find says that the Friedmann-Lemaitre equations describing evolution are indeed adjusted, but by a part in 10 to the fifth. We continue. I remind you that these fluctuations around homogeneity in the curvature are real. Here, a very dense region in which you see curved arcs, each of which represents a background galaxy. This galaxy is in fact back over here some distance. The light that reaches us was initially moving somewhat away from us, got bended by the mass concentration in this region and headed toward us in a gravitational lens that is very imperfect. But nonetheless, you see, these curvature fluctuations are real and they're small. Seconds of arc to tens of seconds of arcs, roughly 10 to the minus 5. We should remind ourselves that we do have a linear relation between redshift and distance, discovered already in 1929, predicted 2 years earlier by the Belgian Georges Lemaitre. The discovery plot doesn't look all that impressive, but within 10 years, Hubble and Humason had extended the plot to redshift 0.1, as you see in the upper left. It took another more than half decade to extend the next factor of 10 to get the plot lower right, about which I will speak more later. We have a linear redshift distance relation that is consistent with an expanding universe, but by no means implies it. How do you know that the universe is expanding? Couldn't there be a tired light phenomenon? Well, doesn't seem likely. But if expanding, is the universe evolving? Certainly in the 1940s, we had a brilliant alternative explanation from Fred Hoyle on the right, Herman Bondi, Tommy Gold, perhaps spontaneous creation of matter. It is important that we have a fossil that shows us that this picture of steady state, the classical steady state, is wrong. We have thermal radiation that fills space. The problem with, yep, very good. Shown here is a spectrum of the sea of radiation that fills space with very small fluctuations. Frequency along the horizontal axis, intensity vertical. You can just barely make out the theoretical Planck function running along the curve and down. This solid curve is a measurement, not a theory, from the Canadian rocket measurement and the US satellite measurements of a decade ago and more. Notice the exquisite precision by which this curve, the measurements follow a thermal curve. Notice the number of orders of magnitude, 3 in wavelength, a lot in intensity. It's a gorgeous fit. Since our universe as it is now is transparent, we know that because we can see distant radio sources, we can be sure that this thermal spectrum could not have been produced in the universe as it is now. Here is tangible evidence that our universe was at one time in a very different state, dense and hot enough to have been able to relax to thermal equilibrium. Notice also that there's a very serious demand on evolution from that earlier time to the present. It has to preserve this spectrum. Within a metric theory, that requires standard electromagnetism, and it requires quite close to homogeneous expansion and quite close to homogeneous initial conditions. If inhomogeneity were present, then we would be viewing mixtures of spectra of different temperatures. That's not what's observed. Tangible evidence also, therefore, that our universe has evolved in a very close to homogeneous way. That evidence does not require general relativity theory. To test that, we need other tests, other cosmological tests. The relation between the luminosity and the sky of an object with given intrinsic luminosity and its redshift was worked out in the 1930s. It took 3 decades before Alan Sandage worked out how the test could be applied using the great 200-inch telescope on Mount Palomar and observing galaxies. And it took another 4 decades or so to complete that test with observations of supernovae. The result is rightly celebrated, but it takes nothing, and here it is shown, redshift, magnitude, upper left, supernovae of a type that can be reduced to a fixed, pretty close to fixed intrinsic luminosity, curvature away from what you would expect in a universe without a cosmological constant, and particularly curved away from a universe that is the simplest of all possible, the universe we would adopt surely if we were a committee, Einstein de Sitter. It fits rather a universe that has a cosmological constant that is expanding with increasing rate, with increasing time. A celebrated result, here an earlier prize to these 3 people, Saul Perlmutter, Adam Rees, Brian Schmidt, and this past week celebrated again with the Nobel Prize. Gorgeous result that here more recent data shows is exactly correct. Now let us remark that it takes nothing from this great accomplishment to ask the question, if we had only the redshift distance relation up to through the supernovae and the thermal spectrum of the microwave background, what would community reaction have been to the indication of a cosmological constant? My thinking is, surely conservative people would say, well, you have done a brilliant job. I'm sure you've checked very carefully about the properties of those supernovae and how they change with time, but you've certainly made a mistake. Some subtle effect has altered the intrinsic luminosities of these supernovae as functions of redshift. Two simple reasons. If lambda is not zero, then the only natural value from quantum mechanics is tens of orders of magnitude too big. And if lambda is the indicated value, it means that we come on the sign just as the cosmological constant is becoming important. An absurd coincidence. Coincidences happen, but this is absurd. You've made a mistake. That is why it is so very important. Oh, and then finally, I should stress one important point. It would be quite justified to ask why we should trust the implications of this measurement. Why should we trust the extrapolation of general relativity theory over so many decades? We trust them because we have other cosmological tests to check the result independently. On the left, again, the distribution of galaxies nearby. On the right, the fluctuations in the brightness of the microwave background across the sky with the mean subtracted, the fluctuations of part in 10 to the fifth at maximum. On the upper left, the power spectrum of the large-scale galaxy distribution. Recall the square of the Fourier transform of the space distribution. You see wiggles. On the upper right, the analog of a power spectrum for distribution across the sky, the square of the spherical harmonic expansion of the brightness temperature as a function of position. The solid curves, a theory, lambda CDM, a gorgeous fit to the data. This fit requires some hypotheses, dark matter and dark energy. This curve alone does not require dark energy. It requires, because what is measured here is largely arising at decoupling. The angular scale at which what happened appears depends on the angular size distance. You can trade angular size distance between Hubble constant and space curvature or cosmological constant or the like. You nail down the length scale, the Hubble constant, by the fact that these oscillations in the galaxy distribution are at relatively short distances, so you know the angular size distance really reasonably well, so you fix a length scale, and therefore you fix the length scale required here to require a cosmological constant. The key thing about this, well worth stressing, this is a totally independent way of looking at the universe that again forced us to a cosmological constant and dark energy. Independent. Those who think that the supernovae have some subtle systematic error must admit that we have here a strong confirmation of a theory that is looking very good. I have lumped here a bunch of other cosmological tests that I'll discuss in just a little detail. I could spend all of my allotted time and then several more lectures just reviewing these tests. For example, we have lower left the color magnitude diagram for star clusters. The star cluster contains stars that are all very nearly the same age. They differ largely in their masses. Different stars with different mass evolve at different rates. Plotted horizontally is the temperature of the surface of the star, hot on the left, cold on the right. Plotted vertically is luminosity increasing up. Two different means of converting from the colors measured in the sky to surface temperature. The stars, in a gorgeous plot, follow this diagram. Position on the diagram indicated by the mass of the star. A gorgeous fit. This fit requires an age. The age is 13.5 gigayears. Take the current expansion rate given to you either by the measurements in the previous slide of anisotropy and inhomogeneity, or from the astronomers who measure the expansion rate directly. Take that expansion rate, and you find that if you don't have a cosmological constant, you find that these stars are older than the universe. Again, independent evidence pointing in the same direction. We should look at just a few more. Here is the spectrum of a distant quasar. Here are the absorption lines shortward of the Lyman alpha resonance of atomic hydrogen. Here are the many absorption lines due to clouds along the line of sight. Here is one of these clouds, the spectrum greatly enlarged to show you the absorption line at the Lyman alpha resonance in that foreground cloud of hydrogen and heavier elements. Here is a little notch, deuterium. The ratio of deuterium to hydrogen depends in the hot Big Bang theory for the origin of the light elements on the baryon mass density. The higher the baryon mass density when conditions were right at temperature to make deuterium determines the amount of deuterium. The higher the mass density in baryons, the more the deuterium is burned out, the lower the residual deuterium. That therefore gives us a baryon density when elements were forming. We know the present temperature, so we know the present baryon density if this theory is right. That baryon density can be compared upper right to the baryon mass contained within this cluster next to it. This from X-ray measurements of the hot plasma that's in the center of this rich cluster. You know the mass in this cluster if you trust the inverse square law. You get the total mass. You may compare it to the baryonic mass and check it against check that against the baryonic mass required to fit. Let me see if I can say that again. You know the plasma mass from the X-rays. You can add in the stellar mass. You observe that in this cluster, things are big enough that you might expect to find a universal relation between dark matter and baryonic matter. Knowing the mean baryonic dark matter, you know the baryonic dark matter, which you can compare to this measurement. You see I'm getting tangled up because these are very complicated, but you get the point, I'm sure. These measurements look at the universe from many sides. That does not mean that we have the final theory, but it means we have an awfully successful description. So my conclusion is the network of cosmological tests is so very well cross-checked that the case is persuasive. We have a good approximation. I've stressed time and again now that I don't think that means we have the final theory. That would be quite against the history of development of natural science. Rather, we have a good approximation. We are working hard to improve it. We can now pause and reflect on how one might proceed to improve a good model. One way, which I think is very sensible, is to stick with what you have until you're forced away from it. That's a little different from the attitude that general relativity theory is such an elegant, logically compelling theory that it must be right. I believe that we are adaptively favored to like that which works. And I quite believe that if you find a better theory than general relativity, better in the sense of more successfully fitting the observations, then you will learn to like that new theory and find it logically compelling. Instead, I think the real reason to stick with the accepted model is you will dissipate a lot of time if you run after every possible alternative. Focus the effort until you're forced away from it. But there is another possibility: follow interesting ideas for alternatives. We saw how the classical steady-state theory stimulated research. In fact, it simply enraged some astronomers so much that they worked very hard to prove it wrong, in the process, of course, greatly enriching our cosmology. Some ideas are remarkably successful. Consider that Einstein's idea of general relativity theory has survived to the present time, an amazing success story. His idea of homogeneity has survived to the present time. Ideas are important. These days, we have ideas such as inflation and modified gravity. They certainly are stimulating research. Whether they are going to be more productive and lead us to a still better cosmology, I think is yet to be determined. I'll be remarking on a few of these issues later. And the third route, Seek anomalies. Ask what phenomena seem rather curious within the standard concepts. If the phenomenon is curious and you examine it closely, you may find either that the anomaly is only apparent and therefore you will have learned something about the standard theory, or else, just possibly, and you understand you're buying a lottery ticket here, just possibly you'll find the anomaly is pointing to something new. I propose to give you an example now of the last. I am very taken with the progress astronomers are making in studying galaxies, now known in such rich detail that you can start to ask quite penetrating questions about the nature of our ideas of star formation and galaxy formation. And let me see, I keep forgetting which way to go. Ah, here we are. Here's a galaxy nearby, seen face on, rotationally supported. I draw your attention to these dark lines. That's dust that is obscuring starlight. Dust tends to settle to the disk of a galaxy. Therefore, the stars must be close to the disk in order that their light may be extinguished. Here is an enlargement of the central region. You see way down in here, you can still follow the dust lanes. Since the dust is in the plane, so must be the stars. This is a giant whirlpool, flat, up to a relatively tiny star cluster in the center. A gorgeous beast. Here is an example of another one. This one's seen edge on. You see the dust lanes. You also see a wonderful arc of starlight. Apparently, a small galaxy has fallen through this guide, being tidally disrupted, and its stars strung out on streams. But only 1% of the light is in this stream. The other 99% in another whirlpool. Here, this can be compared to simulations. These simulations are the Aquarius pure dark matter simulations of Volker Springel et al. Each is representing a region that is going to develop into a galaxy with about the mass of the Milky Way, which is to say the mass also of those pure disk galaxies I showed earlier. The galaxy, our galaxy, by the way, is also very close to pure disk. Plotted here is the following. Consider those dark matter particles that are within the nominal virial radius, that is to say, dynamical equilibrium radius, at the present epoch. Label all those particles and plot them in all earlier plots. Particles that are outside this region at the present time are not plotted in any of the plots, but they're still present, of course, simply not shown. The particles that are inside a radius of 7 kpc, which is about our distance from the center of our galaxy. Particles outside are plotted in gray tones, as shown here. Particles within 7 kpc and outside 3 kpc are plotted in black, and particles within 3 kpc are plotted in yellow. That is to say, this black circle is about the size of the visible part of one of these big galaxies. And inside the yellow part is the central part of that galaxy. Now you ask yourself the question, where is this material at redshift 3? You see the material that is within the virial radius is largely in these white things, but you notice that material that now is well within the galaxy was spread out over all of these lumps. This is fixed physical scale, by the way, and the scale is 600 kiloparsecs, if I remember, 800 kiloparsecs, fixed in all graphs. And I got the wrong one here. I'm having trouble with this. Somehow I'm missing, well, this one is the one I meant to show. Yeah, okay. So, 3 examples. They're pretty typical of the 6 that we have. This is half the sample. The rule, material is now in the galaxy was spread all over the place at redshift 3. Not all the material that is within this region will end up right at the center at the present time, but a good fraction of it is, enough of it to black out the material that didn't end up there. This is the merging that is so very much a part of galaxy formation within lambda CDM. Now here is again the first of these cases. This you already saw. This shows the distribution of dark matter without the color labels. This is all the dark matter. You see a nice correlation. Where this is bright, there is a lot of dark matter, and where it's bright, there's a lot of material that ends up in the center. It's a standard rule of thumb that if particles that are in dense regions at high redshift end up at dense regions at low redshift. Now, notice the star formation history. This is the rate of formation of stars per co-moving volume as a function of time, going back in time. Notice that it peaks up at redshift around 3. At redshift bigger than 6, it's quite uncertain. It drops from redshift 3 to the present by about a factor of 30. This is when the bulk of the stars were being formed. You have to remember that there's a shorter time elapsed here, so that in fact half the stars are formed about at redshift 2. Half the stars formed later. Lots of stars are forming here. Where are they forming? Not entirely well known, because we don't understand star formation, but it seems a likely guess that they're forming where the density is high. Where else would you form stars? Surely that's reasonable. If that's the case, then the stars once formed and acting thereafter like dark matter particles are going to end up here. That is to say, a good fraction of the stars in our galaxy, those that are old, are predicted to have formed splattered all over the place. Now, here is an example of what the consequence. Here, we take the material in the dark matter halo. We assign stars in proportion to the star formation rate globally. So we're assuming that per unit mass, stars form in the halo at the same rate as they do in the cosmic average. We ask where those stars are now. They are spread out in this wonderful sheets and, well, arcs, sheets, spread out very widely. That is to be compared on the same scale with this edge-on galaxy, which is shown here with H1 contours, let's ignore those, and with little drifts of material. Notice a striking difference. The theory is predicting that there are lots of old stars around our galaxy. Where those stars end up at the present time seems to be in a diffuse halo with a considerable fraction of the mass of the galaxy. That's not what we observe in these thin disk galaxies. Instead, the material is concentrated to a disk. The only way you could get this material to end up in a disk is if it were in a disk at high redshift. If it were, as indicated here, spread out all over the place, then as it falls into the galaxy, it's not going to arrange itself into a disk. It'll fall in from all directions and form a more or less spherical halo, rather than what's observed. And so, we have a puzzle. I propose to go on and speak of another puzzle. Here, wonderful data from the Sloan Digital Sky Survey showing vertically color, red galaxies here, old red star populations. Down here, blue galaxies that have young star-forming populations with young stars that are hot and therefore blue. Cool and old, hot and young. Horizontally, luminosity increasing to the right, bright, faint. 3 samples, galaxies that are in low-density regions, high-density regions, and very high-density regions. Some neat astronomy that maybe general relativists need not concern themselves with, but still it's neat. Notice this blue cloud is most intense here and fades away as you go to denser regions. Galaxies that are still actively star-forming like to be alone. Well, it's a neat rule. I don't know that it tests general relativity, but it's nice to know these things. Here is a correlation between color and luminosity in this so-called red branch. Notice that the red branch extends further to the right as you go to denser regions. Massive galaxies like to be in dense regions. That's predicted by lambda CDM. It's seen with great clarity here. Notice finally that there is a correlation between color, that is to say age or metallicity, and luminosity. This line is the same in each plot, and notice it's a good fit to the color-luminosity relation for the galaxies, no matter where they are, in dense regions or low-density regions. Here is an amplification of this, a study of the galaxies in the most underdense regions the astronomers can find. Very lonely galaxies. Here is the blue cloud, heavily populated, continuing the trend you saw earlier. Blue galaxies like to be alone. Here is the red branch, and notice there are red galaxies, red and dead, out in the voids, and they sit where they ought to. That is to say, if you decide to be a red and dead galaxy, then given your mass, your luminosity, I can tell you your color, independent of where you live. Independent. How in the world do these galaxies decide to establish themselves as a given population, independent of environment, when the theory is predicting such violent mixing of environments? This curious behavior might be pointing to something interesting. A speculation that lambda CDM has to be adjusted to make galaxies form earlier, so that when the galaxies are forming, the differences in environment are less pronounced, and so that the material that falls in later is less abundant, so I will be able to form thin disk galaxies, and I will be able to form galaxies in the red and dead sequence that are not so interested in their environment. Not so interested because they formed when the environment variations were much less pronounced. I offer an example of how this might be done. Oh, I'm sorry, somehow this clicking is not working. I'm going to have to go up here. In fact, first I'm going to have to get the, oh. Somehow I left this out, but never mind. More of these statistics. Beautiful. Let us consider modifying general relativity theory, or the standard model, in a simple way. Start with lambda CDM. Add to it, take nothing away. Standard general relativity, standard cold dark matter. Add to it a new class of matter, which I will call evanescent dark matter. This new class of dark matter interacts only with a new scalar field. Here is the scalar field kinetic and gradient energy. Here is the interaction with the particles. The scalar field is simply the mass of the particle. Here is the action for the particle, the kinetic energy term. It's a freely moving particle with a mass that is a function of position. Write the scalar field as the mean part, homogeneous part, and a density and a fluctuating part. From this action, you get an equation for the mean scalar field of this form. I have only particles of one charge, and therefore the scalar field is being driven towards zero. That's a good thing, because I want to make the scalar field vanish at the present time. That means the particle masses vanish at the present time. That means these particles are relativistic, and that means we don't see them. They're just a stream going through. I want to not avoid any conflict with the cosmological tests, and that's how I do it to start with. There is an equation of motion down here. The rate of change of momentum has two terms: gravity, mass times gradient of the gravitational potential, and the gradient of the energy of the particles. So there's a gradient energy term from the gradient of the mass. The gradient force term enters into the equation of motion. It is determined by the field equation for the field fluctuations, which has a gradient term, a del squared term, just as gravity, but it also has, for the gravitational potential, is the mass density fluctuations in the new scalar field, in the new evanescent particles, and in ordinary dark matter. This term gives us a fifth force. That fifth force on small scales is larger than gravity by the ratio of the Planck mass to the scalar field mass squared. That can be a very big number. This evanescent matter can have a strong fifth force while it's present. That's on small scales. where this term dominates in this field equation. On large scales, this term is small compared to this, and the fifth force gets suppressed by the ratio of kT over A. That means this fifth force is important only on relatively small scales within the Hubble length as a function of time. On large scales, it's suppressed and not going to seriously affect the cosmological tests. I give you now an example of the effect of this. Consider a spherically symmetric mass concentration. Adjust parameters so that the scalar field value at high redshift is given by this expression, which is to say it is small compared to the Planck length, which is to say I have a very strong fifth force. The mass density in the scalar field is phi times, in the evanescent particles is the mass, which is phi times the number density. That is going to be about 10 to the minus 4 times the mass density. These numbers are contrived so that the scalar field reaches 0 at a redshift of 20. That's when these particles become relativistic and go away. As the particles are before redshift 20, the particles are attracting each other and running towards the center of any mass concentration and forming a center of attraction for dark matter. This is a situation immediately after redshift 20, when the evanescent particles have become relativistic. They leave behind the distribution of dark matter that has a cusp near the center. That cusp, you understand, is in the conventional dark matter. It was driven there by the cusp in the evanescent dark matter that has now gone away. The result is I am forming protogalaxies that have knobs in the center. That could have all kinds of wonderful properties. It is a remarkable thing that high redshift, that at redshifts, 8, there are very massive quasars that seem to have black holes of mass 10 to the 9th solar masses. Puzzling that these massive black holes form so early. But one way to do it, of course, one way to do it is to say this would be a very good way to catalyze the formation of a central massive black hole. Once that central massive black hole is formed, it might be a good place to gather stars to form an old stellar halo, which we know is correlated with the presence of the massive black hole. I could go on. I won't, because in fact I haven't done much more than this. We will just dream on. And in any case, I don't think it's appropriate to press this idea now. I instead offer it as a worked example of the fact that it's easy to adjust the standard model without affecting it. Perhaps you have done similar adjustments. It's also the fact that it's easy to find adjustments that are aimed at apparent anomalies, real phenomena that seem to suggest you should consider an adjustment that works within the standard model and yet does something new and interesting. That is to say, it's pretty clear to me that this subject is in a very early state with lots to be done. And I now conclude with a series of concluding remarks, comments on what I think we have learned. First, general relativity theory, along with the rest of physics, passes a really demanding test. I've emphasized that, and I'm still deeply impressed by it. It means that we have an example of how, in natural science, ideas can have enormous power. This particular case, the extrapolation of general relativity, is persuasive because cross-checked by so many independent measurements. On the other hand, there are viable alternatives, and I do stress that good science demands that viable alternatives be pursued. Second, the case for dark matter and dark energy, I think it's persuasive for the same reason. We have checks from many different directions. Of course, we don't know what the dark matter is, and although we often think of it as something very simple, cold dark matter or maybe warm dark matter, there are lots of alternatives. Maybe it's annihilating, maybe it's interacting and or annihilating, and or warm, and or hot, and or evanescent, and or something completely different. Pause to consider that if we could observe the visible sector only through its gravity, we would puzzle out many aspects of the visible sector, but it would be a pretty crude approximation. Surely the same is true in the dark sector. I have to mention the alternative, MOND, modified Newtonian dynamics. Seriously problematic. How in the world can you get those acoustic oscillations into matter and radiation distributions without dark matter and dark energy? Problematic as could be. On the other hand, I really have to admire its treatment of galaxies. The search for evolution of Einstein's lambda has become a very big topic. Lots of resources devoted to it. That's very good science. I must say, though, that I feel uneasy about the great focus on a notion that has no theory behind it. I can say that because my friend Bharat Ratra and I worked out this evolving lambda many years ago. We never put it forth as a theory. It was at best a scenario. This search for evolving lambda is not compared to the LHC search for the dark sector. There is a deeply tested and tightly constructed theory. It means to me that we really should not slight exploration of broader ideas of how to somehow formulate and test properties of dark energy. I have to remark that the curious value of lambda supports interest in anthropic arguments, in multiverses, and I just have to say, in my own personal, very old-fashioned point of view, I fear this as the onset of the age of data-free science, which I would hope to avoid living through. The case for inflation is very important. We need to have a theory for what the universe was doing before it could be described by standard general relativity theory. It is by far the most well worked out case. It's readily adjusted to fit statistical homogeneity, the hot Big Bang, near scale invariant Gaussian initial conditions. On the other hand, all of these things are kind of generic in the sense that they were all discussed before we had inflation. Much more specific to inflation is tilt. However, I remain unpersuaded that tilt has been actually detected. It is usually said to be detected at 3 standard deviations, although a few people using alternative methods of statistics get 2 standard deviations. Also important is that it does depend on the reionization history. And as I check it out, one can postulate early reionization that at redshift 30 and above would recombine and give you, remove the evidence for tilt. In short, this is going to require yet more work. Perhaps Planck will make a big contribution to the case. There are the prospects for gravitational waves, non-Gaussianity. All that is always for the future. My conclusion is that we don't know yet whether inflation really happened. That's for the future. And finally, I am these days very much preoccupied with the notion that research on cosmic structure formation, from highly redshifted 21 centimeter to galaxies at high redshift to the nearby galaxies, is going to be a fascinating field and one that does test our cosmological ideas. Rich in data, productive. And then finally, I will conclude with a personal reflection. I got into this game a half century ago. Where did the time go? I had no idea. I was very uneasy about getting into this subject because it was such a schematic field at the time. I had no idea things would turn out in the rich way they have. One may get the impression on thinking back on how greatly cosmology has changed that my generation worked out all the easy problems and left all the hard problems for your generation. There is some truth in that, for after all, the subject was so schematic then that a modest advance was a big fractional change in what we knew. But it is also quite misleading. I can assure you that the problems we faced then didn't look at all easy. Instead, we had to learn how to formulate them and how, by formulating properly, address them. The historical record convinces me that you are similarly going to find that the problems you face in this subject are not nearly as complicated as they look once you have learned how to formulate them properly and how to address them properly.
Actually, it's not so much of a question as more of a comment. I mean, you made the remark at the beginning that the conventional steady-state cosmology has, of course, been ruled out. I think everybody would agree with that. On the other hand, inflation somehow could constitute a resurrection of that, of course on a very different timescale. But many of the same ideas are there, certainly the same philosophical basis, and the idea of particle creation out of quote-unquote nothing.
It's a good remark, and indeed another example of the power of ideas. Though as we should bear in mind, that is a very different time scale. Also, yet to be demonstrated to be a good approximation to reality.
I have a question. You showed Sandage's predictions of the redshift magnitude diagram. And I believe it's true that in the steady state that the prediction would be for Q naught to be -0.5, which is more or less what we observe. So I'm asking you a kind of hypothetical question. If the supernova work or some other measurement of the Hubble diagram had preceded the cosmic microwave background, wouldn't we have taken that as evidence for the steady state theory?
I wonder. The steady state theory was never very popular outside Great Britain, was it?
You're asking me?
I was a graduate student in those days, and I didn't hear favorable remarks about it.
Right.
There would have been resistance. Well, that may well be a selection effect. There would have been resistance, just as there would have been resistance to lambda, the other interpretation. I don't know how people would have reacted. But in fact, I guess that illustrates the main point. One measurement does not a theory substantiate.
Right, I think you're right, that it's the context of all of this stuff taken together that
Yes.
really helps you make sense of the measurements, even though, working hard on making the measurements precisely is an art in itself.
It is, and important, you won't get to the second stage, the cross-checks, unless you have the first stage, the careful measurements. But they're both necessary.
If the choice is between an unnatural value of lambda and a large void which violates the Copernican principle, how are we to favor one over the other unless an experimental test comes and tells us which of the two is a better alternative?
I believe you have in mind the idea of a radial density gradient
Yes,
with us in the center.
yes.
One can only appeal to the other measurements. For example, one has the baryon acoustic oscillations in the distribution of the galaxies, which is at redshift 0.3, and one has the analog, the acoustic oscillations in the radiation temperature, which are produced at redshift 10 to the third or higher. The consistency between those two does, of course, have a free parameter in it, the time scale. But then we have astronomers who measure that time scale, and we get consistency. So that void can't be outside redshift 0.3, where the galaxies are measured. That, of course, is indirect, but this whole game is indirect, and it is the network of evidence that is so rich now that leaves rather little room for that. Then again, you pause to consider, oh, well, no, I'll stop there.
Hi. Coming back to the galaxies, you showed us evidence that the color magnitude diagram does not really care about the environment. How was the environment defined in this case? Was it through nearest neighbors? Or
I'm sorry, I didn't.
how was the environment defined
Oh.
in the galaxies case? Was
Yes.
it through nearest neighbors, like the fifth nearest neighbor? Or?
Some use nearest neighbors, some use counts out to a greater distance. And among the experts who do these studies, you will find sharp discussions about which is the best. I think it doesn't matter to us. It's a qualitative difference. There are statistically low density environments and high density.
Right. No, but the main problem is that you're looking at environments today and not the environments when these galaxies were formed, right?
Yes.
And that's a big difference because...
Oh, it is a very big difference, and that's why you want to form the galaxies when the environmental differences were small.
They're small, right.
Which is to say at high redshift, and not what is suggested by lambda CDM, where there's that pummeling of material at low redshift.
It does not necessarily mean that that galaxies, well, galaxies get assembled and larger galaxies get assembled at larger redshifts, right?
We should be careful of assertions.
Right, yeah,
We are being phenomenological,
right, yeah, sure.
and we are observing that a galaxy doesn't care about its environment. There are strong exceptions to that, of course, but by and large, a galaxy like the Milky Way doesn't care where it is. And that requires, that is a very pressing demand on the cosmology.
Okay, Jayanti, and then there's a question back there. Jayanti?
Are multiverse theories testable? And if yes, then what are the few tests for multiverse theories?
You'll have to repeat more slowly.
Are multiverse theories testable?
I ask you. And if not testable, are multi-universes part of natural science? It's a very difficult question.
There's a question at the back.
I wonder if you can comment how much confidence you place in the deductions from black body nucleosynthesis. It seems to me like a few years ago people were saying the best fit was less than 3 neutrinos. Now in recent months I've seen some papers that say we need more than 3 neutrinos. So what should we make of this?
I wish I knew. The qualitative point is, to me, the more impressive. We need about 3 neutrinos, which the particle physicists assure us they have. The finer details may be problems with systematic errors, or just possibly with physics that might be slightly adjusted. To me, it's entirely thinkable that there are minor adjustments, small adjustments to be made in the cosmology, perhaps in the gravity physics, perhaps in the behavior of dark matter, that would have an effect on the anisotropy spectrum of the radiation that implies the number of neutrinos I think you're mentioning. All of this is possible. Possible either that it's a systematic error or an error in the theory, but I'm thinking that if it's an error in the theory, it's a small error. Yes? Are you thinking of sterile neutrinos?
Dimitri,
Report that result.
Professor
Don't
Bala.
you agree?
GM is working nicely as a phenomenological model, but it has some problem with the physics, theoretical physics, because actually we know that 95% of the components of the universe is not explained. And therefore, which is most important for you? Phenomenological model which works, or something which had nicely grounded theory for the physics, which is explaining the model.
Yes. I think you know me well enough now to understand that I would vote for the phenomenology. And I mean it not cynically. Once you have a theory that is very successful in the experimental tests, you will learn to like the theory. You will find reasons to like it.
Professor Wali?
You made some very interesting comments about the natural science and how it proceeds. Obviously, we start with observations, which we select the observations that we can make and find a suitable approximation that then can be incorporated in mathematical structure. And mathematical structure predicts new things. And then we again observe, excluding other things, only testing the predictions made by that particular solution. So it worked very well for a long time, but as more and more technology advances, the selection of what you observe about nature depends so much upon our mathematical ability to formulate in the mathematical terms. So my question is, are we describing real nature or mathematical nature?
Are we developing a self-fulfilling a theory that is guided by its success to approximations of the same theory. I don't think so. We have so many people doing so many experiments. In each of these groups, I think, would be delighted to find an anomaly. They would have something new. I don't think there is any tendency to hide disturbing results. That is why I celebrate the evidence for super relativistic, supersonic, whatever, superluminal neutrinos. You've got to report these anomalies and then take the heat. I believe the community by and large does report the anomalies, and I think that is the correcting factor. It will mean that things are discovered that we cannot have predicted because we didn't understand the mathematics. But that's very healthy, wouldn't you agree?
David, and then.
I wondered if you had any comment about whether warm dark matter was a better or worse modification to cold dark matter than, say, the evanescent dark matter?
It may be right. Historically, it's interesting to remark that the warm dark matter model has come and gone in fashion, not for any reason of evidence, but for convenience. Cold dark matter is just simpler, one fewer parameters. I don't know whether warm dark matter will solve the problems I have in mind. It is introduced, I believe, to lower the number of low-mass galaxies, a subject that has been heavily debated. Maybe there are serious problems there. Maybe warm dark matter will solve them. I don't quite see how it would solve the problems that I'm complaining about. And of course, part of the art of finding a new cosmology that is better will be incorporating many of these phenomena, finding that concept that has more than one result. Introducing one parameter to solve one problem is not always attractive.
Prasad.
What can we learn about the dynamics of dark matter from the phenomenological success of MOND?
Wouldn't I like to know? MOND, you recall, has a wonderful feature. It predicts the circular velocity of a galaxy as a function of its luminosity. It was invented at a time when that relation was very sketchily known. Since then, the prediction has held up to the best of our ability to measure it. It's a wonderful success. It stands alone, though. You can't fit MOND, as I understand it, into any cosmology with all of the detailed tests we have. So what is the lesson from MOND? I wish I knew. I think we should keep MOND in mind, but only in mind.
My question is regarding how do you personally, in the presence of competing scientific methodologies, of having a fundamental theory of lambda Q-sinium, would you want to go in small steps in terms of small steps of understanding a theory, or understanding a theory in a whole way, in a fundamental way? In two scientific competing methodologies, what do you prefer as a scientific worker?
Yes. By and large, we advance in very small steps. Historically, isn't that the case? Small increments with the occasional big jump. I don't think we program what will happen. We make small increments because it's possible. We hope for big increments, big steps, but we can't predict when that will happen. I think it would be a mistake to focus on either to the exclusion of the other.
Okay, one last question from Surud.
So this is regarding MOND again. Don't you think it would be interesting to understand why MOND works in the framework of lambda CDM?
Oh, yes, I do. If you have ideas, you should follow them up.
Okay. Okay. Oh, you should be on record.
Yeah. There is a way of understanding this, which I think very long back pointed out by Mike Turner. If you look at the power spectrum of galaxy in lambda CDM, it has a peak, and you can also plot the power spectrum for the acceleration, gravitational acceleration. And then when you compute it, you do get a characteristic acceleration scale, which is related to h0, and because of a strange coincidences, the numerical factors work out fine. So at some zeroth level, we know why there is a preferred acceleration scale, which is related to the Hubble constant of today, which is embedded in the galaxy formation scenarios. Rest, I believe, is a question of details.
Well, we should be a little careful. We have adjusted the parameters of lambda CDM to make galaxies that have the properties that are reflected in MOND.
Okay, TP.
If I could just add, my student and I have a poster just outside this door which explains why MOND works.
Excellent. Thank you.
Okay, so on this note, let's thank Jim Peebles again for a wonderful talk.